Okay. Yeah, thanks a lot for the invitation to speak. Right, so I will talk about p-adic functors on rigid spaces. And before I talk about any functors, let's start some motivation for why I want to do this and what I want to do. So usually the motivation for functor formalisms in any sort of geometry is that you have some homology theory that you want to understand, and you have some basic questions like reality and so on that you want to prove. And in this case, setting your ends for geometry is really hard. Some break with those. Non-accumulated field over QP. Okay, and X smooth proper smooth rigid variety of C, let's say a pure dimension. Okay, so I guess X is an analog. This is a p-adic analog of a complex manifold complex numbers. And then because you could expect there to be some sort of pro-étale for cohomology on that space, and statements as follows. So it's now then for all integers I greater than or equal to 0, there is a natural perfect parent of the ith the cohomology of X with coefficients like L. And I carry with the 2D minus I cohomology. And carrying will go to some papers, essentially just that. So this is now a known theorem, and let me maybe say something about the history of the proof. So there's two major cases. So the first case was proved quite a while ago, was the case L not equal to P. In this case, it was proved independently. Which and I'm not that well prepared. I forgot to write down the dates, but it was 1980 or 90 something. So I guess you could say it's passable or not. But the case L equal to P is more involved. So I mean, even though the field itself is characteristic 0, right? C is characteristic 0 field, the case L equal to P is hard, and we will explain in a second why. Because I have some K topology in there. Right? So P is somehow hidden in the topology on that. And so this was proved. The first one by Colmez-Gilles-Niziol. And the idea is, so I mean, this is part of Daniel's thesis, but based on previous ideas by Gamma. And the proof goes by studying local models formal models of these things. Okay, so in the easiest, in the easiest case, when X has good reduction, so it comes from you can find a model of a ZP that is smooth, such that this is just a generic fiber. In that case, I think the proof is essentially due to Colmez from the 1980s or something. And then if it does not have good reduction, then we need lots of steps just to reduce that case. That's essentially what we do. And now there's a second proof. Using full formalism. Or roughly FP sheaves on X. And the advantage of having a full functor formalism is, of course, you get much more, right? So you get similar results for non-proper X, more general use. And just FP, so for example, you can take your favorite local system if you want, and the relative setting. Okay, and well, I guess you can guess that the goal of my talk is to present you how this works. And well, depending on how it goes, I might also talk about similar constructions that work not only for FP, but also ZP and QP. But for today, I want to focus on the FP case. And yeah, so maybe let me make one remark on why this is complicated compared to the other mathematical case. Comes from the fact that the cohomology coefficients in FP often depends on the base fields. Okay, so that's similar to what happens if you try to do a p-homology on characteristic P sheaves, steves. You take the p-homology of A1, and the thing is not only not finite, it's huge, and inside of it you see lots of things that come from the base that you look at. And that basically kills any sort of base change you can look for. Because of course once you're on C, there's nothing happening anymore, and there's no base change that you can work on the field. So what is the general idea of overcoming that difficulty? Well, I have to work with a more general version of coefficients, which takes into account
so what should I write in my note? Should I say that there is no base change for the, or should I write that there is no naive base change?
Well, there is no base change for a p-homology.
And nothing to replace.
Well, I will replace it by something, yes.
So okay. So at least the kills naive.
If I have a 600 formalism, then there will be base change.
So this kills naive base.
Yes. Well, take the cohomology and then have them like this. Like this, so you can take the cohomology here, you can pull it back here, or you can pull it back into the cohomology, and that will not come. And you might say, okay, we just good for two fields, maybe that's not so bad. But if I want to have a functor formalism, I want this kind of base change also. I don't know, maybe some relative situation pass through some field here or something. And these sort of base changes, they become very problematic because these commodities depend on the thing you're working on.
But just to clarify, is that because you were working with something that was not proper, like A1? And
yes. Okay. Well, for A1, actually, I think it's okay. But locally, my rigid variety is not an A1. It's disk maybe. Locally, I think looks like a disk.
So you're saying that the easiest counterexample is a disk.
Yes. You can take
Or already one disk. One
those disks dimension one, and if you compute the cohomology using the usual Anschütz sequence.
So the first cohomology.
I guess. Yeah. Don't ask me for details about that. I did that about it. But yeah, you certainly see lots of things happening that I don't see. Okay. And okay, you might say for the cohomology, when there's not necessarily phase change, you only expect it for cohomology with context support. But in the smooth setting, these things should be rated by duality. So one of them fails, probably also fails. Okay. And so what is the idea to solve this? The strategy solution. Work with some sort of quasicoherent things. Thanks. Okay. More concretely, roughly, we will associate the effects on analytic stack. Let's maybe call it X. And okay, analytic stack is terminology in this condensed framework of Clausen Scholze, but in our setting, will just be our algebraic stack. And then such that the call sheets on X and that into quasicoherent sheets on that stack. Okay, and if we know this, and we know a little bit about how they embed, then we can use this example formalism that we have on quasicoherent sheets to get something we can work with. And of course, it will, in general, get you outside of this category, but that's okay. And once, if you understand that embedding well enough, then you know in which situations you can expect for the 600 remaining here. So that's the general idea of what I want to do. And maybe formulate it in maybe the modern language. And that's actually the general paradigm that Clausen Scholze seem to have nowadays. Whenever you want to construct 600 formalism for anything, what you should try to do is try to find the appropriate stack and then just get quasicoherent sheets on that. And I guess this is maybe one of the first examples of implementing this. Sorry.
Of the elliptic, more classical elliptic setting. I don't quite understand what stack means in this context, but is there a certain stack behind the usual six-functor formalism in Clausen-Gilles?
No, not yet. Not yet. But Peter is very pleased. So I understand. You can even hope to get this promoted. This is all conjectural, very, very.
But the more classical, I think this is only.
Yes, the problem is if you have a specialization on a scheme, just take a stack of some variation in where you have specialization. Then top sheets on that are really hard to write as fast as sheets on.
Okay. Do you mean by algebraic in this setting? Again, having some smooth cover by some regions for the visibility of the diagonal, or?
I originally mean that it's a stack with final schemes.
Oh.
You'll see later what it will look like. And It will not involve rigid geometry at all. Like, the
Okay,
fact
so
is
even though
that
X,
so
even though X is.
X is a rigid variable,
Right.
and the thing I associated will be a scheme in characters of P. Well, not a scheme, but
So for some people, the word stack means algebraic stack. For other people, it means abstract stack. It's a sheet of characters. So when you say stack here, so are you saying that this will be an algebraic stack? Or does that functor and
I mean, I guess I'm not really making any claims about
algebraic? So it will be a functor on the category of from a functors from schemes to bullets
yes.
with a sheet problem. Step.
I mean, probably you can show more, but I didn't care too much. I mean, the way I will present it, I will not literally write it that way. This is just like one conceptual modern view of what you should like, how to look at it. And in my thesis, where all this comes from, I formulated it differently, and I guess I will present it differently as well. But I will remark at the end, like what that stack might would actually be.
So just note. So you have revealed some kind of. So it will it be a thing which will be explicitly used, or it is a secret behind yours?
I find it easier to not think about it in terms of that stack.
Okay. So technically you will some slightly.
Yes. Well, I will associate to X some category which you might call quasicoherent sheets to some sense. And that is, I guess, the formulation that makes it most precise. Right. But I will usually just talk about that category and not care too much about the stack behind it.
Is it the case that the coherent cohomology of this computes the p-adic cohomology of X?
Yeah, that's exactly the point. Yes. Right. Yeah, so that's what I mean by you need to understand this embedding so that you know the homology here, then it will get the homology effect. Homologies I will come to that later. First, before, I mean, yeah, you already said in the beginning, but I should maybe say a little bit about the condensed stuff. So I claim that there's a 600 formalism for quasicoherent sheaves and such a thing. The quasicoherent sheaves are mean in this solid condensed framework. So I thought maybe the first thing I should do is give a quick introduction or recall for what this, how this works. So what I mean by this quasicoherent. So, well, this is part of the condensed mathematics framework of Clausen Scholze. Let me maybe first recall the definition of condensed linear groups and condensed modules. Maybe say make the remarks, but maybe you should think about them. So, it's actually quite easy to define. You have found just the category of sheets. On the side of profinite sets. So this protein is the side of profinite sets. There are covers such as finite jointly surjective families of sets. Obviously, but then you can also identify this as the pro-étale side, just a geometric point. Maybe I should remark that now Peter and Dustin have shifted perspective slightly and only consider the full subset here where you only have those small and countable limits of finite sets. But for what I'm going to talk today about, it doesn't really matter. So I'll just stick to this. That's going to be all.
So let us disregard that issue.
Yes. So if you can pick some color here and then it's fine, and that's totally fine for everything I'm going to talk about. So this is category of I call it condensed behaviors. And I'll usually not care about the region category. I'll go to the derived category throughout. So, you know, and maybe this mutation is slightly provocative. I fully embrace the condensed settings, so the here see is derived category. And so you should think of objects in here as some sort of topological Abelian groups. So they're Abelian groups that have some topology on them, so the multiplication is continuous. But in fact, so example, so every topological Abelian group B induces a condensed Abelian group. The underline, which is just a functor that sends proponents at S to the set or Abelian group of maps from S, continuous functions, continuous maps from S to G. So somehow you should think of an element in here as capturing exactly what are the continuous functions for proponent sets. In the easiest cases, I take a proponent set that's just one point, and then maps from there to here, capture the underlying set of G. But now if I take more complicated proponent sets, then I understand how they continuously map into my space. I understand a lot about the topology. And like the idea of this condensed setup is that that's exactly what the topology should be in the first place. It's just capturing how proponent sets map.
Yeah, so we are thinking of build topological space, which can be captured by maps from components. So we compass them, and then this is essentially equivalent to considering totally discontinuous. Profile.
Yes, yes. I mean, this is, yeah, taking all profile is equivalent to taking all. So it makes sense as this functor.
Can you repeat the last sentence?
Sorry?
Sorry, can you repeat the last sentence? Is that one?
Instead of taking the side of profinet sets, you can also take the side of compact Hausdorff spaces. So you take the same covering, additional coverings. And turns out that profinet sets are the basis of that. So,
Yeah, so the essential point is that you can represent any compact set. The compact space, for me, the compact always means contour, unless specified. You can represent any compact space as a quotient of the profile.
So
For instance, the segment 01 can be represented as quotient 10% by using decimal extensions. Only people don't like the number 10. You can use.
Okay, and because I'm capturing exactly the maps from the compact Hausdorff and profinet sets, it's not surprising that this functor is fully faithful. On compactly generated Abelian groups. Okay, and if you don't know what compactly generated means, here's an example. Metrizable. So most of your favorite ones are in there, probably all of them. Nice. Unless you do something very weird, it's hard to come up with a non-compactly generated. Okay, so we capture really the thing that previously was only captured by topology, but now in the setting, and the big advantage of this condensed Abelian framework is that it is an Abelian category, unlike the category topology group. So I can form the derived category and I can do derived stuff. And that's crucial, of course, if I want to do cohomology and so on, I need to derive stuff. Okay. Then a condensed ring, a condensed string, and maybe even animated. But if you don't know what that word means, just ignore it. Okay, so condensed ring just means ring and ring object in that category of condensity groups. So it's condensity group together with the multiplication. You know, you know, it's just the modules over A. And you know, okay, so that's the category of derived category of something like topological modules over the topological ring. Just topological in the sense of condensed mathematics.
I have a question about the order, right? Because in theory, you have animated things, you can find but you can find like condensed of animated things, right?
Yes.
And you can also do like animation.
Yeah, it doesn't matter.
It doesn't matter.
Should be doing something.
Oh,
Animation,
That's-
visualization. Right, yeah, so you have these two axes, right? You have the derived axis and the condensed axis.
so they are.
And these things, they have both information. I mean, all for all of this is true. Also for the derived effect. Elements in here have derived direction and condensed direction. They're somehow dependent. So you can first introduce the one and then the other. Like I can also define this as the condensed category of the usual category, derived category. So like maybe if you're scared of this derived infinity stuff, maybe let me just say that the only case we're interested in today is a discrete, so just a normal, non-derived ring. P of A is literally just to derive category from sheets. A modulus from okay, so nothing should be too scared of. And well, notice that. So note two things. So first of all, D of A has a tensor product and internal one. Okay, that's like but true for any shapes on any sides. And also D of A is compactly generated. By the three guys, and I have three modules. For a certain special class of profile sets, like the disconnected sets. Okay, maybe I don't want to go too much into detail about
What by A brackets X.
this is the sheetification of the functor. Goes to a
For S and what is for S?
okay, sorry. So this is extremely connected. That's a special type of profile set and exactly the projected profiles. But I guess
So for instance,
Also, just to clarify, this is one of the things that becomes a little bit more complicated in the light setting.
right. Now the last setting, this category is not complex generated. Yes, I guess that
in
was
what setting?
this new setting where they put some cardinals on the profile. I think that is the biggest, like, the biggest disadvantage of it. But it makes a lot of other things easier, so I guess that's why it's switched.
But for the solid setting, it's
It
not.
doesn't matter, the solid setting is completely generated, don't have a range. Okay, so now we have a good category of topological derived A models. Okay, so that's good, but it's still not enough because, well, the tensor product is somewhat stupid. You can easily check that the tensor product, if you evaluate it on just essentially 1 point, and that tensor product is just the tensor product of the things going on this 1 point. So it completely ignores the topology of that structure. And I want to change that. I want some sort of complete tensor product. So let's introduce this. That's where the solid stuff comes in. So the definition for
So I would think that this the problem you can just define is relevant only as a part of a definition. So you will use it to define and this is the only purpose of this naive.
I guess so. I mean, it fits into general theory that allows these rings, these categories, and also the solid ones that I will introduce now. But for my talk, I only use the solid ones. And I'm not aware of any application of this naive kind of product.
Yes, so just one more thing. At some point, when you have many, when I hear many definition of this type, I usually get lost until I get something. Maybe real life examples. So probably you have no choice but proceed this way. But maybe eventually, so probably there are some naive ideas behind all this machinery and its applications to your additional problem. So at some point, I think you have to, if you want to understand something, then mention these naive understandable ideas and somehow emphasize them, because there is a danger that people fall, summarize this, fall asleep. And but when something simple and important happens, then you have to wake us up.
Well, I have to introduce the solid version, and then I'll give an example, try to explain why it solves all your problems. Okay. So maybe there's one more definition. I can get this complete version. So for A, it is straight. Ring, we let be solid. Okay. The full subcategory generated. So Colmez for certain completed versions. I mean, everything in here is a co-limit of these guys, and I know how to just complete those. So I define new versions, which I call a solid of S. Okay, the definition looks a bit weird, maybe. I take a co-limit over all subrings of A, which are finite type, over Z, and then for each of those, I take a limit over A joined Si, or all profound sets S, which I write as a limit ESI. Okay, and
Sorry, you probably want to have A prime at 27.
oh, sorry, yes.
So this square is a symbol which should be very solid.
Yes.
Okay. And
I mean, originally Peter invested.
well, it's for us. This is the law. But anyway, so this definition of T solid is limits of such thing.
Right.
And now You are giving the definition of a solid number.
Right, I mean, okay, the idea is I want to replace this guy by some complete version. Okay, how can you complete this? Well, S is a limit of SIs. So I guess well, one obvious thing how am I completed, especially selecting the limit of but then for some technical reasons, I have to do this I can only do this in the case of finite type of Brazilian. So in general, I have to take the full limit of that.
Yeah, I will honestly write it down, but I hope that you understand it's impossible to understand such a definition. To understand such definition in real time.
Right. Well,
I can only the only thing that I can is to write it.
Okay, so one is when you say columns, do you mean like the localizing subcategory of in general, do you mean like the localizing? I mean, the subcategory.
Well, I'm saying that can be full limit of these.
Okay.
But I mean, these will be the company generators as well.
Okay.
That's
Wait, I mean, I get but sorry, so is the reason that the reason that the definition is this way is so that you get an analytic ring? Is that right? And also is it right? So part of so in general, this is a property on an object of D of A. So if you have an object of D of A, it's a property for it to be in D solid.
right, exactly. Yeah.
And the point is that the property only depends on it only depends on it having the property for every finitely generated subring.
Yes. Right. So the inclusion. Don't worry, I will try to make them slightly more concrete in a second. I just thought it would be nice to get the formal definition.
There was a completion somewhere, and for all the so suppose that A is already a finite type of C, then
Yeah,
what
you just check this.
projective limit of
Right, but this is the limit in condensed sets, so let's still have the limit topology.
Can I take this walk? Sorry, we're going to say this, but I just like found this intuition kind of helpful to think about like solidity, which is that a solid module is supposed to be something like a linear topology. And like okay, so if you think of condensed Abelian groups as corresponding to some generalization of all topological Abelian groups, then a solid Abelian group is something like a linear topology. So the topology defined by subgroups. And so, well, I should say complete linear topology, so it's complete for topology defined by subgroups. And being in D solid of A should really mean that it's in some sense, well, let's say if A is finitely generated, then it's like we have an A linear topology. So it's the topology is defined by a family of A modules. And okay, so I guess being in D solid of A for A arbitrary is saying that you have this condition for this sort of linearity of the topology for every finitely generated subring. Like, isn't there also a way of saying, I mean, there's some sort of expression that an element of A should have sort of spectral radius at most one, and like every element of A gets an endomorphism of your object with D of A, and being in D solid of A is equivalent somehow equivalent to well being solid for each of those elements, so being solid over Z bracket X for each of those elements, and that I thought was supposed to there was some intuition that's having spectral radius at most one.
Yeah, something like this. Okay.
yes. So probably most of us learned something from functional analysis. Some of us learned logical. So whenever there is a way to, well, for instance, I know something about functions. I know something about the kind of algebra states which so if there is a way to illustrate.
Yes, I will try to. I wanted to
In some vague cases of where so say classical functional analysis applies would be very helpful.
I will try to give an example in a second. I wanted to complete the definition first because the point was to really find the transit stuff. I haven't done that yet.
Yes.
So let me do that first. and then I'll say something. So the inclusion that of categories that I have there has a left adjoint. That's then the completion factor. And so I call this the solidification. Or okay, maybe I'll notice tensor over A is very solid. So that's the functor that takes P of A to be solid of A. There's the Coulomb preserving functor that just sends A and S. There's solid. Yeah. And we can now redefine the tensor product. Over A solid to be, well, I take the tensor product over A, and then I can do. Yeah, and then we get our example.
I think you have some point the word completion or something like this. Does this functor has a name? This functor has this left adjoint, does it?
Yeah, solidification.
Solidification.
Sorry, yeah, I think maybe I should have put the word solid somewhere, but
Well, left adjoint form is
okay. So to give some examples, so first of all, we note that actually A is finite type over Z. So where we don't need this weird co-limit, then the same solid S has a very simple form. It's actually just problems. Okay. So I depends on S of course, but you can always write this just as a product of copies of A. So you don't have to really, I mean, these objects are extremely simple. And you basically just take A modules that can be written as columns of products of A. That's essentially what this solid category looks like. And so to give some examples of solid stuff, also.
Sorry, what is the I?
Sorry, what?
What was the ivory part?
Oh, some set.
Okay.
And it depends on the size of S essentially.
Here, do you require S to be externally described?
No,
or
and yeah, S can be any program.
any program?
Also, D solid of A is stable under limits.
if it's finite type, then the solid of S is what? The product of A.
Right. This thing you can write is just a product. This is saying something like continuous functions in a profinite set are really, really good. But it's essentially implies it.
But it's a product, not a sum. So,
Yeah, it is a product. So it has the product topology as an A model, as a condensed A. So you can embed it via this embedding. From the topological A module given by the product. Yeah, so basically all you have to understand is products and co-elements of those, and everything you can build out of that is awesome. Yeah.
Sorry, this isomorphism of condensed A.
Yes. I wanted to give one example. So let's example ZP and QP. So there, there's a stable in the limits and co-limits, and I can build those as finite discrete stuff. Right. And if I make the solid tensor product, then this is 0, P is not equal to L, and that's ZP. So I mean, that's the easiest case, and also maybe something that hopefully convinces you that this is not a stupid theory. So it does what we want, right? I mean, the sort of tensor product seems to understand the topologies with respect to which these things are complete and matches them together. And if they're not compatible, it just kills them. Otherwise, it gives you the thing that you expect. Yes?
Sorry, so when you write A joint S, is this free object in the sense of abelian groups, or?
Yes, I mean, this has a pretty finite, so it's really just this pretty finite.
Oh, I mean, like, do you consider this A prime and joint SI as like the abelian free A prime module, the set SI, or do you consider this like free homomorphic object?
No, it's just a pretty, this is just finitely many copies of A as a module, free as an A module. This is not a polynomial. Okay. But then maybe let me also mention that you take R and you solidify at 0. So it does not factor the completeness of R, it factors more like profinite completeness.
And yeah, so you are saying that R is
And this is the solidification, right? Okay, and so let me now come to the quasicoherent sheaves and this example formalism. Why do I do this? I mean, so far I'm just playing around. Okay?
Yeah, sorry, one last question. And just A solid is A solid and S when S is just.
Oh, a solid here is really just a symbol. Yeah, you can give a solid some meaning. I don't really want to do that, but right. I mean, for me, it's just a symbol for now, and a solid S has a meaning. And tensoring with a like this symbol up there, this is solidification. And you can give these things a meaning so that it's an actual object and the tensor product.
Okay, it's like an actual object, like the image A, right?
Yeah, I mean the A solid, like A inside of the A is solid as an A module, right? So inside of the solid of A is just solid A. So for a map of rings, I can consider the solid phase change, which is just the tensor up, and then I solidify over B. Okay, so this takes a solid A module and makes out of it a solid B module. So I do have a pullback, or just the usual phase change of solid modules. And once I have this, I can glue to get the category D solid of X, or any scheme X. Okay, then I call this solid quasicoherent sheaves. Right. And now there's the theorem due to Clausen Scholze. And by gluing, I mean gluing, and I'm gluing the derived categories since I'm infinity category sense. So you should think of an object in here just to cover your scheme X by F lines, and on each F line you take a module, and then you have some descent data around that. And on each F line I take just this D solid of A.
So just to clarify, there's a result that you're using about the D solid of A satisfying.
Yes, of course. Yeah, to make this work, you need that D solid of A satisfies descent, or it's a risky colors. Yeah. But that's not too hard. Okay, and the theorem by Clausen Scholze is that there is a functor formalism consisting of the beautiful 6 functors. So we have a tensor product, an internal hum, pullback, push pullback, lower streak, and upper streak. And these I will define for all that. And these are well defined for finite type. For this category. You saw it. In other words, one sub has to bring. I guess you probably know that it's the usual category of derived schemes, of quasi-coherent sheaves and schemes. I don't really have a successful formalism, and the main problem being the lower Schritt can't be defined. All the other functors, I guess, are fine as clear setting, but the lower Schritt is a problem. And the key observation they made is in the solid setting, you can define a lower Schritt. And let me.
So for me, when you say solid, secretly replace it by topology.
Complete topology.
Complete topologies.
But, well,
and of course, then, and then,
I mean, QP, for example, is solid, right? But it's not really complete in any, it's not adequately complete for any adequate function.
yeah.
This completeness notion is by definition stable under Colmez. So you need to be a bit careful, but yeah, roughly it's complete.
Yeah. Sorry. I want to think of this derived solid category as quasi-convergence, right?
Yes.
So if I remember correctly, if your map is not quasi-compact, quasi-separate at lower.
I
think
think it's okay, but if you want, then maybe assume QCQS.
Because I think for quasi-convergence, I don't think it's right.
Well, here it is by definition because I defined the lower star just as the right adjoint. Okay, sorry, maybe I should have said that. Right? So upper star is just the fallback that I had based on this. Lower star is just by definition the right adjoint. Okay, and these two I have to construct this. And the key observation, like if I want to define the lower Schritt for a proper map, of course I just take the lower star. So I need to define it for an open immersion. And well, suppose I have one. So suppose I have spec A at 1 over A, open immersion into spec A. What should be the lower Schritt? We want this map to be homologically étale, of course. In other words, the upper Schritt should be the upper star, so the lower Schritt must be the left adjoint in that, right? So we take a lower Schritt. It's now a function from U solid A adjoint 1 over A to U solid A to be the left adjoint. The upper star. And why does it suddenly work? Well, why does it not work classically? Well, I mean, all of these categories are nice. So for this left adjoint to exist, all you need to check is that the whole vector will limits. I claim that it does now, whereas it didn't in the classical setting. Here's my quasi-coherent sheets. What's the point? Well, so for this to work, we need there the star into this. Goodness. This is not true classically, but it is. This classically, okay, just some product, copies of A, and then tensor it. And one over A, and now this is not. One over A. And so this is classically where the theory breaks down, but suddenly it works. And you can see it, at least if A is a finite type with Z, you can see this case directly, right? Because this is just public generated, associated to some finite set. But there is one person I have that. And the solid tensor product will preserve contact generated, so it will send this to the contact generator for A one of A. So here's how it works. I think that was one of the key insights that Clausen Scholze had. So you have this example formalism, and I'm finally done with this exposure.
Sorry, can I one quick comment? Question. But is it correct that when you say schemes here, do you mean derived schemes?
Oh, yeah.
Sorry, it's otherwise like when you form base change.
I might forget to mention derived, because everything here is implicitly derived, I guess. Although the cases that we need at the end, they are not derived. Yes, for the most part, you can ignore that.
And sorry, what goes wrong if you just work with schemes?
If you want base change to work, so if you want like lower, like, I don't know, for instance, if you plot a map, you have lower star, upper star. I mean, in the easiest case, that would just amount to some base change for rings, but because I have derived modules, I need the tensor product of rings to be a derived tensor product, so I need to allow that.
I guess classically, this is like people call cohomology base change. Yeah, like that.
I think it's preserving somehow related to this strategy that we rather than the actual.
I think it's more like. I mean, that it really depends on the solid version. I mean, if I do the same with this, it doesn't work. I really need to fix my contact generator so that I have this particular shape. Okay, so let's get back to setting the I actually want to talk about. I wanted to construct a six-functor formalism for p-sheaves on rigid varieties. And I call this section protective geometry because, as I will explain in a second, you will have to pass the protective spaces in order to construct this.
So, one quick comment. So we're about an hour in. So at some point, it's not too much longer. We should have a break.
Maybe now it's a good time.
Now it's a good time. Then we can.
If we're going to take a break.
I'm sorry.
Okay, so let's get back to rigid geometry. We have all this knowledge about solid classically here. Now I want to apply it to study of p-sheaves on rigid spaces. And well, first question is how do we relate a p-sheaves to anything classically here? And there we can use, or at least as a motivation, we can use Scholze comparative theorem and let it call that. Scholze's primitive comparison.
Sorry, can I ask one?
Sure.
So you wrote this key observation of how you define geometry for a distinguished organ. So how do you do this? I mean, like if you have any open U spring A, how do you differentiate?
I mean, if you invert more elements, or I mean, if you have an open finite coupling, it's just finite limits. So these are stable indicators, so everything can use with finite limits of elements, so that shouldn't be an issue. I mean, I just like I define it as for not emission, I define the lower trig as the right left adjoint of the upper step. I can take it as the condition. So all I have to check is that the upper step is its limits. And actually, the way I prove that is that in the distinguished case, I explicitly construct the lower trig. That is how they prove that it exists. But now, if you have a more general enumeration, you can cover it finite in many distinguished ones. And then the upper star. All finite. Any finite volume element these volumes. That's the issue. So what is the primitive comparison theorem? Well, that x be as before, so x I guess this is maybe somewhat optional. operate on rigid-analytic over C again. And then which also proved is for all I is hypermorphic to 0, the I-étale homology coefficient at P is finite. And more importantly, there's classically a version computing that. And if I take the P homology and I tensor that over FP with OC not P. So OC is the ring of integers, the elements of normness with P1. I take that mod P, that's my P algebra, of course. Take a tensor, and then there's a natural map from this to the homology of the sheet like mod P. So I don't know how familiar people are with rigid geometry.
With what?
Rigid geometry in spaces. So maybe
I can tell you about myself. Many years ago, learned the theorem of rigid spaces.
right.
Before their college.
I need them to the edit version.
You need the edit version, it's Huber's. Okay. So I heard it many times, but I don't have the hard knowledge.
Right. But that's why I wanted to quickly recall what this thing is.
But this one, for this statement, wouldn't any of the theories work the same?
Yes, but I do need edit spaces like that.
So
Was it all expressed? I think it's maybe something that is more akin to the
just so X is in Fate's world of rigid space.
yeah, as long as it's proper smooth, it doesn't matter which way.
Yes. But now you Scholze compares it with something else. Now, what the first? Let me first write down the statements and then probably they will contain some words that I don't quite understand, and then we will explain the meaning of it. But first of all, you.
So I'm going to edit the sentence. The reason I didn't want to do that is because there's another word that I'll come to that.
Just a moment. OX plus mod. So what is the what is the what are the words and symbols beyond Fate's set? Yeah, the left hand side. Well, suppose I know what type of poetry is.
No, I think that is the same as
what is OX plus? If X X is still in Fate's, what is OX plus?
right. So I think I should define almost an OX plus. So let me. So X exactly what is X plus? Well, one way to define it is it's a sheet, of course, on its top. You can define it as all partitions in that. What's the value of X? This is actually okay, but for this, I mean, I make it look very simple, but for this relation here to have any meaning, I guess it's probably best to work in the article. Okay, maybe
but just why do you need the edit world here? If X is the rigid space in the sense
okay.
it's any space in Algo, but it's still in this world.
Okay, I guess in this case it's probably okay.
So in this case, so far I understand what's going on. Now the next thing is to explain what it means in almost as.
I mean, let me make a very quick remark. I mean, okay, first of all, this is still a ring, right? Because being estimated to 1 and it's not actually insane is something that rings are stable in there. So this is the ring I came out of at P, then it is the sheet of the p-adic. And also note that this OC is exactly the OX plus for X, which is point X. So it's the same right here as here, essentially. Okay, what does almost isomorphism mean? Well, this means that the kernel and the kernel of this map are filled by all elements epsilon in the maximum ideal. Okay, and it's an ideal of OC, but I touched it to see it.
Occurred by the next validity. And what would be
Right, so
no, for any just no, killed. But if by each by any epsilon, but
So what does this mean? I mean, what does this ideal generated by? Or you can generate it generated by, well, P is in there, of course, and you can get 1/2. Third, that's not. And if you continue this, and that will be a generated sequence for this ideal. Okay, you notice that these get very close to 1. Like if 1 was in there, and of course, being killed by 1 is the same as being 0. And I'm saying the kernel and co-kernel, they might not be 0, but they are killed by anything that's arbitrarily close to 1, in the sense of being slightly bigger power. And I'm really using here that C is not right because this ideal would be.
Is saying so you wrote Q by epsilon in is this the same as saying Q by MC?
Well, I guess so. That's what you mean by killed by MC. But I mean the product difference is 0.
So when you say that, usually when you say that something is killed by ideal, also means that it was killed by any.
Yeah, then I guess it's the same.
Yes.
Yeah, so there's almost thing, or there's almost property due to essentially due to this here. This will now we will have to use this everywhere from now on. This almost version. But I guess for the most part, we don't have to worry too much about this. For the most part, you can just take this. You can just ignore it. But yeah, to be precise, you need to. Okay, so what do we get out of this? Well, we notice that the p-cohomology on this side can be computed by this cohomology about expressed by p, and this looks a lot more close to p than right. So this goes in the right direction. So the idea is to replace the category of the top sheets by something like solid quasicoherent.
I have a question about this. Maybe I heard this, but so the first question is there a progress map? So you said that this map is an almost isomorphism. Is this map?
The map should be natural.
It's yes, I believe that if you say that it's not this, I believe it's not this. But then the next question. So suppose that X is let's say unit disk, the unit disk. I want to understand what I suppose that p-adic is fine. So then I know how to compute H1 by and now, and what is the right hand side in this case? Is it can I understand? So,
I mean, maybe, oh, sorry. Yeah, okay, yeah, sure.
is there a way to so maybe it's not the right way to think about this theorem, but still, so I want to but it's proper, it's proper.
Right, I mean, in the case of the unitless, this is wrong.
So there is no way to test it in the field.
I think whenever this is my
So
part,
there's-
I wouldn't focus.
So there's no hope to proceed this way. Okay. I'm sorry for this interruption. I here replace that by solid.
I mean, we notice that the cohomology here can be computed by the cohomology of this, but this looks, I mean, this is quite close to some sort of structure sheet. So you get that we can define something like quasicoherent modules, and of course I take the solid version because of those 6 functors over that ring.
Yeah. But as you say, this theorem is specific for proper states.
Yes.
And you want to develop the 6-functor formalism, which requires non-proper spaces as well. So I'm a little bit how, but this theorem is only a motivation.
I will actually, part of the thing I construct will reprove the theorem, I guess, more generality, although the theorem exists before more generality. So I don't think I actually prove it in much more generality, but it will fall out of this extended form discussion. So I don't have to put that in. It's really just motivation for why I want to do this. You'll see at the end when it's just possible.
Can I just a question or comment with the theorem? I mean, is it correct that this is an analog? Like if you have a proper scheme over over an algebraically closed field with characteristic P, then the étale cohomology, the P coefficient, if you extend scalars to K, is the same as the coherent cohomology.
Yes.
The artificial sequence, and this is some sort of analog. It's somehow sophisticated analog.
I guess it's a bit more sophisticated. Yeah, it's somewhat amusing that when I wrote my thesis, I think this is the first time such a version of the 6-functor formalism was constructed. Somehow amusing that I do it in this case. I guess for schemes, maybe it's easier and more natural to comparison. I mean, that for schemes, functionality wasn't really possible. And as far as I know, there's also no written reference for doing similar construction schemes. I guess someone should do this at some point. Using like a similar idea.
So you were saying that the reason is that there is no such stimulus theory for schemes.
As far as I know,
That nobody cares. Not so.
I shouldn't be, I mean, the same technique that I use here should be applicable, and probably these guys.
He asked me, maybe I asked another question whether there is similar theorem for electric sheaves flat else.
Yes, I mean,
Then the answer is no, and this is not because nobody cares about this.
I think some people care a lot,
But because it's not clear how to get.
unless you work over characteristic zero coefficient. In some cases, you can, of course, check this, but if you're in P geometry and so far it's not going to do it that way. Somewhat amusing. I guess maybe 5 years ago, like the p-adic case was beating the hardest one. Now with this modern approach, this seems to be like the one that works the best, and the other case is not.
Yes, there is a similar surprise. The surprise is that the crystalline cohomology developed after the time of the so in some sense, it is simpler
Yeah, I guess that's very simplistic.
So if I understand, I remember correctly, this how it's supposed to be in policy shows this paper, they're classical equations, right? Just usual equations. And now if you go solid quasi-coherent, it's not pretty much just do you want to think about this question like the next step?
Oh yeah, derived solid.
Sorry, but I mean like the question.
I mean, this thing has no p torsion, so the question is not derived. Okay. So we have this. So I want to define this. Okay. But now the problem is, so the main obstacle is that this sheaf OX plus E is not cyclic locally. In general, of course, in the text point there is important, but in general it's not. So so I mean, if you want to have a good theory of quasi-coherent sheaves in any space, then locally quasi-coherent module should just be a module over something, right? But for that to work, you need that on that local piece, there's no cohomology. That's basically fine. That way. But unfortunately, this thing has always been not true cohomology. So, for example, the ball has not true cohomology. So it's not acyclic, so there's no that you can just look at that. So how do we solve the problem? Well, the solution.
When you say the wall, you mean the disk over.
Yeah, sorry.
It doesn't fill already for one disk, for one disk.
So the solution is to pass the factoid of this key. We use quasi-coherent sheaves and pro-étale molecule. I will say a little bit about the factoid in a second. I just wanted to recap what I mean. So I say locally on X-étale, this thing is not acyclic, but you could hope that if you're well more covered, then suddenly it does become acyclic. And the answer is it does work. And the kind of coverage I need to allow is basically tolerance of these moments. Because then things become perfected, and then suddenly it works. And I will explain that.
Sorry, like the cyclic, you mean like almost the same, right?
Yes.
Okay.
So that was the perfected space. I will not give a proper definition. I just want to say roughly what it means. So I mean, this roughly means that all functions this one. So, okay, in other words, if you have a function on a perfected space, then there must be another function which is very close to being a free fruit up to some epsilon, and that epsilon can be made arbitrary. I will give an example that should hopefully illustrate what I mean. And next, let me see the torus. So it's just the space associated to CHI and PT inverse. Then we can take perfected torus, which is C, D. I'm going to take all the p to the answers, and the same as the inverse. Just the x. So this guy is not perfected. This map is very hard. Okay, so the fact that this map is pro-étale, you can see because I can just join just p to the n first and then increase n. And if I join p to the n first, it's a path. So just take the limit of that. And then this thing is perfected, well, it comes down to the fact that I have joined all the p to the n first of the coordinates. Okay, so that is kind of a basic example of how one can cover a rigid variety by the vector space. And I think you should roughly see this as covering space by some sort of universal cover. So you should see this perfected cover as some sort of universal cover in space.
Well, the universal cover is almost.
It's almost set, yeah.
The universal covering of the say is canonical if you choose the base.
Yes, okay, not in that.
But this thing is canonical and so this analogy is not
in that sense, but in the sense that you study this space by covering for something that is extremely simple.
So this example, there's no epsilon. Didn't work.
I mean this epsilon?
Yeah.
No, but if you want to take p2 and first of any element in here, you can have to.
but just so in C you can take the root of essence. Here you are saying that you cannot make it. You cannot we do not have the size of the root, but you can do it.
So any algebraic plus fields, of course.
Yes, but here you do need the
Okay. Okay, so this suggests studying rigid spaces by the vector spaces. And well, Clausen has written a little paper on how to do that. So let me quickly introduce this notation. So the definition is that we consider a new category p stack, which is best defined as stacks on the side here. Yeah.
So maybe for certain people. So is having making eight roots and deep roots up to some epsilon with literally the difference between being perfect and something perfect, right?
So there's no
there is zero, so perfect.
It doesn't mean.
Well,
I mean like modulo B, right? Modulo B you have perfect, you said like when you consider perfectly algebra.
Well, if you just think will not be perfect.
Yeah, but it's something. Yeah, for me, it's perfect. So this is the difference between like getting all functions of meeting different versus having all.
No, but even though C mod P is not perfect. C
just C mod B is symmetrical.
I guess that is one way of
but why do you need epsilon that is the example? Suppose that let's consider so So there is a question, at least, so if you consider the features,
Mod P is selective, so you can take the root mod P. That will only work up to P. One over P or something. Then you have this error where you can try.
so what is there, if I take the image, O plus the functions with what do I get? Do I just get around the windows in the T in fractional powers of T with coefficients in C mod P? And if so, then why is it a thing of subjective on the nodes?
It is. In this case, it is.
In this case, it is.
Mod P it is. But it's not here.
I see. It's another X. And it was legitimate. So you are saying that
Like mod P is.
yes. So if for Frobenius, the reduction of low P Frobenius is subjective on the nose in this particular case. And then you can somehow perceive
Exactly. So I take this how do you repeat stacks? So let me introduce. So what would we need here? So perf is the category of perfected spaces. P. The retopology, the one that's generated by just subjective maps of QCKS spaces. Okay, so it's essentially something like the FPQC topology, except that you drop the flatness hypothesis. Has some quasi-compactness assumption, but right. So it might be a bit weird that I consider only perfected spaces in characteristic P, which are just perfect. P actually has all P-grams roots, all P's roots exist in these things in characteristic P. Because here I need to cover it by a space in characteristic 0, right? So I can't really cover it by anything characteristic. Yeah, that's some weird thing that happens here. Namely, I can still embed a rigid variety or maybe let's say an analytic place. With P. Okay, so for example, a rigid variety, if you don't like adding spaces, just think of the same X as I had before. And I claim that there is a functor here, and that functor sends X to X, and then I put a little diamond in the top. And that's how the associated diamond, and what does it do? Next time, the only that constant profile of space S is by definition the set of all pairs until S. And from that until S. And yeah, if you're not used to perfected geometry, that might look very weird. The point is that whenever you have perfected space in characteristic 0, or even characteristic P, but whenever you have one characteristic 0, there's a procedure called tilting that takes on one and makes one characteristic P. Okay, in this case, I just replace C by another characteristic P of the same field, and the same. It turns out this is a general procedure. So for any characteristic 0 for vector space, they can associate a characteristic P for vector space. And that association is more or less a projection. Except that, well, as soon as it gets some base projection. So essentially, I can just work in here in the characteristic P spaces because I can always unfold them with characteristic there. And maybe that's all I want to say about that. It's a bit mind-bending. It's the first time you see that. Can be very confusing. But I guess for now you can also just think of these as splitting in characteristic 0 like Clausen. Then just take the maps. But this is how Clausen defines things. And that's really where the power of perfected geometry comes from, because you can study stuff in characteristic 0 using stuff in characteristic P. And characteristic P are Frobenius and inside or Mann. By the way, it's supposed to go until half past. Or I was told 2 hours.
Yes, here it's 1 to 6 30, but we want to finish.
Well, now I'm in the middle of something. So what? Now I'm in the middle of something. Yes. So, yeah, I'll see whenever I have time to get stuff. Okay. Now, I claim that perfected spaces make things easier, so here's a proposition, but also it makes everything work now, or at least conceptually. It's given a finite perfected space. And so here I'm not really working on this epic setup, but I guess for the most part, you can maybe ignore that and think of these. Well, I guess like the other theories don't really work in this node theory setting. I'll just stick to that. So if X is a finite perfected, then the sheaf OX plus is almost a size vector. I.e. HI X plus is, well, I take the almost version of this. Almost 0 for all. Okay, so you can both, so that finally we have solved this obstacle. We can both, and in these spaces we can actually we can use these as the local ones on which our quasicoherent sheaves such as modules.
Yes, so you formulated the code for this proposition is and we didn't use the notion of these stacks.
Well, except for
this proposition,
yes, I did not, but implicitly in this construction, I claim that this construction is maybe not fully faithful, but it captures the power side of the structure sheet. And well, implicit in that claim is that I can cover X by using out the vector space.
Yes, so the idea is to pass and just to fill X instead of doing elements.
Right.
And then there is a wonderful machinery which allows with the words tilt and tilt, which allows
Right, but that is not so important for what I want to say, right? I mean, this passing to characteristic P helps, for example, proving this. But I don't really need pass to characteristic P.
Yes, but I'm mentioning characteristic P because in the definition of this step, what my understanding is that curve is defined to be the factoid based on characteristic. And the reason which seem to have nothing to do with our original zero x. But when is the magic word magic word
That magic allows us to do things like this. But yeah, I don't strictly need that. But this is like a standard definition in vector geometry. So that's why I copy it. I guess for this talk, you can probably also just take the B side of all the vector spaces and ignore tools. But I don't know, Scholze has written papers in this category, so I'm probably
Yes.
good to introduce that category. Right. So using all of that, so now I want to define how this category classically here achieves. And so if I want to do that, I want them to be modules over all plasma P which locally in the pro-étale or even now V topology, they're just modules of this degree. And for that to work, I need to check that at least in the vector spaces, this glues, right? Like if I have a V cover for vector spaces, then a module over the base is the same as descends along the V cover. And that is exactly what I proved. So this is so that's kind of a key technical result that we need to make all of this work.
So it's a key theorem. It's not just a theorem.
Sure.
In other words, it's a theorem, not a proposition.
Yeah, this is really a theorem.
And moreover, this theorem is the key.
I would claim that this theorem is the one that makes everything work. The rest is just working out details, essentially. But this is the hard one.
Quick question. Is that supported in set of shapes?
No, I mean, not for this, but the fact that I can do this text allows me to study representations by applying this text. So, like, Clausen Scholze have this whole program of Jacquet-Langlands, so they study stuff in that category, and then we talk sheets on that, and what I will present in a second, we can do the same on the. I mean, the goal of all of this is not just proof on radar to the spaces, and for this to work on all these spaces, of course. Okay. So, okay, now I need to introduce. Unfortunately, it gets slightly more technical because I need to choose now the unfold, and I also need to fix the phi because I don't want to stick with my p all the time. So I take a slight variation of the B space I had before. So I consider triples where X is a B space. And that chart the Anschütz of X. And phi is sorry uniformizer. On X chart. Okay, so lots of new symbols. But I guess so the pair of X together with an Anschütz. I mean, these together is basically similar as if I replace curve with just all perfected spaces there. I mean, for example, any perfected space I can view as its tilting characteristic P together with this. Okay, so these together, now these together somehow live in characteristic 0, for example. And Absorption uniformizer is well something that is locally topologically neutral unit. And I guess maybe the most important example of this is equally n. If you're in characteristic 0, but the chosen Anschütz is in characteristic 0. Okay, and this pair you should think of as a rigid-analytic. Okay, so this functor up there gives us some information that if I start with a rigid variety, I can keep the information of this Anschütz. Okay, I haven't really said what I mean by until, but roughly I mean that for any perfected space of maps into it, I choose an until for that. Okay, that's just slightly technical stuff that we shouldn't worry too much about. And then here's the actual statement. There is a or unique autocomplete species going from this category to the infinity category of infinity categories. So to drop the infinity at some point. Just everything is implicitly infinity. And it sends a triple, okay, maybe that's wrong X. So it sends a pair, the category which you denote B solid A OX plus X short multiplied. Okay, so far it's just symbols. Now I want it to be unique, so I have to specify it in some ways. And namely such that for the phenotype, the factored X. So for such a guy, I want it to be just modules over that guy. Oh, 8 plus 1 pi. Unfortunately, that doesn't work. No. I don't have full design for all of them. But for enough, namely, I have to put some condition on it. And namely that it has finite transcendence degree over some probably disconnected. I will say something about these words in a second. Totally disconnected. Vector space. We have B solid A of X plus pi. Pi is any sorry from my line. Is the category B solid A plus. Okay.
So it has finite quantities.
Right, so this is
there.
yeah, this is roughly transcendence degree. I mean, okay. Well, it is more or less finite transcendence degree. Okay, so if I have a map of spaces, then I can look at each pair of points that map to each other, and I claim that the function fields are finite transcendence degree, and that is the condition. And that's a rather mild condition, unless you try to construct something really huge, you'll basically always be in this situation. What does totally disconnected mean? Well, that's a special kind of protective space, such that all of these connected components, so first of all, it's a p-node, and all connected components of the form star A and plus. Okay, protected field. A plus. Open variation. Open bound. Okay, so introduced to the static role, such a space is essentially just a chain of points. So you should think of it as some sort of analog variation. So these spaces are extremely simple, okay? They are just
So many years ago, I think this is accessible. So there are many things here which are excessive precision for me. So I confirm what. For instance, your condition on X is probably very important, but I prefer to pretend that.
Yes.
I mean, we know it perfectly.
I prefer to be precise in the statement.
Of course, we have
You
to be
can,
precise.
you can, for the most part, ignore these things.
Yes, but so let us ignore this. Then, so what you do? You're saying that for an economic perfectoid, you declare that G is solvent of that your the category is just defined as it is solvent of the A plus. And then the problem is when such assignment is achieved in some reasonable sense. And the claim, and again, the word hypercomplete is too difficult for me. You have to say it, but I am keeping it. Then you say that this assignment is a V-shape, and this is the rough. That the assignment that you assign to the X getting the solved A plus 5. Then this assignment is the sheet of and this is the main fact which we expect. Six formalism. Anyways, of course, such a that should be
definition. What happened next? What happened to control?
Yeah, that's implicit if I say, sorry, in a particular space, you can view it as, okay, sorry, maybe I should.
Okay, cool.
Yeah, that's also business